There we go. I started recording the lecture. Here's hoping I can figure out how to download it at the end. Okay, so on Friday we were talking about doing a search through a collection of things that's going to be a lot faster than just a linear search. And again, like I was saying, you've all done this before. Whether you believe me or not, you have, but I can guarantee you have. And I'm going to do an example of this. In order to do this, though, I need a volunteer. One volunteer, and I'm just going to ask you to pick a number between 1 and, hold on, let me see what the number is. 1 and, oops. 1 and, actually, let's do a number between 0 and 1023. So I need a volunteer to pick a number. Someone raise your hand if you want to be that volunteer. Come on, we need somebody. There we go. Okay, Ghazi, if you have a mic, turn it on. But if you don't, it's okay. Just type in the chat. Okay, don't type the number. But okay, so you have a number between 0 and 1023.
Yeah.
Okay, perfect. So here's what I'm going to do. I'm going to share my screen. Share. I'll just share the whole screen. Share. So there we go. And whoa. All right. Well, we're going to go over here. Can you see this by chance?
Yeah.
Okay. What is it? Guess. That's 10. Okay. So I've got 10 tries. Okay. And I'm going to guess a number, the number you're thinking of, between 0 and 1023 in 10 guesses or less.
Okay.
This, of course, is going to be a lot better than the worst case scenario of a linear search, right? Because if this was a linear search, I'd have to look at 1024 things because we have to include 0, right? So this is going to be a lot better because worst case scenario, linear search, 1024. Here, it's only 10. But there's a catch. Okay, I'm gonna guess a number, but you got to do something for me. You gotta say higher or lower. All right, is that fair?
Yeah.
Okay, so here's my first guess. 511, higher or lower, or am I right?
It's lower.
Lower. Okay. 255.
Lower.
127.
Even lower.
Okay. 63.
Even lower.
31.
Still lower.
Okay. 15.
Still low.
7.
Still low.
3.
Low.
1.
Low. Wait a minute. Oh, you're saying that is that number lower, or am I saying that it's supposed to be lower?
Well, you're saying if your number is lower than the number I guessed.
Oh, sorry. I thought you meant that. Okay, sorry about that.
Oh, am I moving the wrong way? Okay, well, maybe we'll try again. So your number wasn't 0, is that right?
Yeah, sorry about that.
All right, let's try that again. Okay, no, James didn't mess up. Ghazi messed up. All right, let's try this again. All right, so 511, is your number higher or lower?
Higher.
Okay, all right. 767.
Higher.
895.
Oh, lower.
Okay. 831.
It's higher.
863.
It's higher.
879.
It's lower.
871.
A little lower.
867.
Higher.
869.
Lower.
All right, well.
Yeah, it's
868. Wow, look at that. And I got it in 10 guesses. Look at that. And we can all agree 10 is much fewer than 1024, right? But of course, I'm going to go back here and we're going to see a giant looking into infinity, but that's okay. I'm going to let's have a look at the chat and we'll see. Raise your hand. All right, by the way, thank you very much, Ghazi, for participating. Raise your hand if, like, you know what I did. Like I'm like cheating, right? Like just raise your hand if you're like, yeah, okay, this isn't that special, and keep it up. I just want to see. So a lot of people. And here's what I mean when I say, I know you all have done this before. How many of you have, and I know the answer to this, how many of you have ever had a textbook and you're looking for page like, I don't know, how many pages in this book? I don't know, let's pretend I don't even know. You're looking for page 421 or something. And how many of you open this textbook and start at the very beginning and go, okay, is this page 421? No. Is this page 421? No. Is this one? No. Is this one? No. I mean, that's the linear search, starting at the beginning and going until we find what we're looking for. I mean, that's ridiculous. No one's going to do this. No one's going to start at the beginning and go look for it. What are you going to do? You're going to go, well, okay, I don't know, maybe it's somewhere in the middle. So you guess in the middle somewhere. And oh, I'm at 412. What was I looking for? 421? Well, if it was 421, I got pretty close actually. So I look at the middle and then I go, okay, well, knowing where that is, I'm going to go this way a little bit, So let's say, for example, I didn't get this lucky and I was actually looking for page like 621. Tell me, this is higher numbers, lower numbers. If I'm on page 412 and I'm looking for page, like 650, I don't know, whatever number I was saying, do I need to look over here? No, absolutely not. That's silly. I look over here because this is where the bigger numbers are. If I know the number I'm looking for is bigger than what I'm looking at, I can throw away like half the stuff here. Gone. I don't need to look over here anymore. So what I'll do is I'll go like, I don't know, halfway-ish. That looks about halfway. And look at that. I'm at page 556, 557. But I'm looking for 650. And I know 650 must be on this side, right? And over here, these numbers are all lower. And I know 650 is not going to be over here. So all of these pages, I can throw them away as well. So over here, okay, I'm going to go a little bit more and be like, okay, what am I looking at? This page doesn't actually have a number. 657. Oh, okay. So I'm at 656 and 657. Okay. So all of these numbers are bigger, and I'm looking for 650. 650 is not over here because these are the bigger numbers. So I know it must be in this area here. So I'll look in here and I'll go about halfway, and so on. I know all of you have done this before. This right here is called, it's not a linear search, it's called a binary search. And it's a really clever algorithm. But what makes it clever is the utility, right? You all know how to do this. Like it's intrinsic, you know how to do this. No one even taught you this, right? It's just you obviously come up with this algorithm. Here, I'm gonna change it so we're not looking into infinity anymore. You obviously know this algorithm. And that's fantastic. But of course, there's a catch. The catch is you have to say higher or lower. And in order to say higher or lower, you have to know that all the stuff you're looking at is in order. I need to know that if I'm looking at a given number, I need to know if I'm looking for a bigger number, then I know which side of those numbers I have to look at. So imagine you had a list of numbers and they're all in order. I'll look somewhere in the middle and find the number. If the numbers are ordered, I can throw away half the numbers and continue looking on the other half only. It's a funny idea, but it's not too bad. So where do we got here? We were talking about the linear search. Okay, activity. So here we go. Look at that. James guessed in less than 10. Fantastic. So the catch is the numbers need to be ordered, because if they're ordered, we know that if I'm looking here and I'm looking for a bigger number, I can look over here. If I'm looking for a lower number, I can look over here. And if I'm looking for a lower number and looking over here, I can ignore everything over here. I throw away half of the remaining stuff. So think about this. I look here, and the number I'm looking for is lower. So I'm looking over here, I can throw all that away. So I'm left with this half. So let's take this half, put it here. So now let's say I look for a number, I'll go right to the middle again. Boom. Is the number I'm looking for higher or lower? Let's say it's lower again. Okay, so I've got these higher numbers and lower numbers. I can throw away the higher ones. And now I've got this small little bit left. And then here, maybe I'm looking for a higher one. So now I'm looking at this small little bit here, and there we go. So every time I make a guess, I can throw away half of the stuff that we had to start with. So you might be wondering, why was I able to guess 10? Like, why did I know I can pick a number between 0 and 1023? Or if we can make this a little cleaner if you'd like. Pretend I was picking a number between 1 and 1024, for example. It's the same range, it's just instead of starting at 0, I started at 1. That might make the math a little easier in your head. So if I'm starting at a number that's, like if I'm halving every time, like why is it that I knew I could find that number in 10 guesses or less as opposed to 1024 guesses? Why? Because remember with the linear search, I start at the beginning. I look at the first thing. Is it what I'm looking for? Yes, no. If not, okay, go to the next. Go to the next. Go to the next. And then worst case scenario, we get all the way to the end. And maybe that thing's not even in that list, or maybe it's the last thing, but that's like the worst case scenario. We have to look at all n things. But why 10? And can we think of the mathematical relationship between 1024 and 10 or something? Like what's going on there? And I want you to take a second. We'll take a brief little moment. I'll give you like 2 minutes and like think about it. Why 10? So I'll give you a minute. I'll give you to like 10:20 or 11:32 to think about it. And then we'll see if anyone kind of comes up with any ideas. So think on that for a second. No, well, okay, you're ruining it for everyone. Well, it's because we count in base 10 system. Okay, that's not quite right, but you know, I kind of like the way you're thinking. And I saw Ghazi had his hand up. What was your question, Ghazi?
Is it can I answer or do I have to?
Let's give other people a second, but we'll let you try first, okay? Let's see. One nice thing about lecturing from home is I can have like water. By the way, is the sound okay? Is it too quiet, too loud? Is it echoey or anything? Someone type. Good? All right, awesome, fantastic. You're pretty clear, fantastic. It's actually quite, ooh, look at those mice. It's actually quite fitting that we're looking at something like this today. Huh. We'll come back to that in a moment, but anyways. Okay, so Ghazi, what do you think? What's your thought? Actually, before you answer, click the raise your hand button to let me know if you think you know. Okay, couple people. Okay, I'm willing to bet if I give you a little bit more time, more people would come up with it. But let's see. Okay, what do you say, Ghazi?
So you make 10 guesses, and every time you kind of like lower it by a factor of half, so it's like half to the power of 10, which is like 1 over 1024.
Yeah. So let's see. In fact, I could probably let's just go here and do that. So like if I say, okay, A equals 1024 divided by 2, right? And then what's that? Okay, A equals A divided by 2. Let's just do that again. Do that again. Let's do that again. Let's do that again. Do that again. Okay. Let's do that again. Okay. Do that again. Let's do that again. Look at that. So like this is telling us like if I half it and if I can throw half the things away, what am I left with? So the first time I throw half the stuff away, I'm left with 512. The next time I throw half the stuff away, I'm left with 256. And then blah, 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 blah. I mean, okay, after 256, we go 128, 64, 32, then we got 16, then we get 8, then 4, then 2, and then 1. And I mean, after we divide the 2 by 2, we're left with one thing. And look how many times I divided by 2. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after the 10th time, I'm guaranteed to have at most one thing left. If this is a nice multiple of 2. We'll come to that later. So after 10, there's only one thing left. I mean, it's possible that I guessed your number before that, and it would just so happen that, let's say I guessed it here when it was 16. Then, okay, great. I found it earlier, and I just got lucky that I guessed the one, like that guess was the one of the 16. But if I keep dividing by 2 and I keep going, and eventually I'll be left with one thing left. So my guess has to be that one thing. And that must be what we're looking for if I haven't found it already. So I think like this is what you were saying, right, Ghazi? This was your idea?
Yeah.
There we go. Fantastic. So this is fantastic. Look at this. I mean, but the catch is we have to have the stuff sorted first. Not that big of a deal. Or maybe it is kind of a big deal because, you know, the point of the linear search is that it takes like n steps, worst case scenario. If the size of the input is n, then worst case scenario, I have to look at all n things. And if I double the size of n, I double the amount of work I have to do. Now, what's the relationship here? What's the mathematical relationship between, let's see, 1024, okay, you know what? I'm just going to show you. So if I take log base 2 of 1024, it's 10. So for those of you that's seeing log and going like, oh no, not logarithms, I don't remember, just they're actually not as bad as you think. Maybe things weren't explained to you well enough, but here's the idea. You know how if you do multiplication multiple times, like if I wanted 5 times 5 times 5, I could just do 5 squared, or squared, cubed, right? 5 times 5 times 5. Well, multiple multiplications is just exponent, right? To the power of. Well, if I wanted like 10, let's say 16 divided by, let's like 2 divided by 2, like if we wanted to do multiple divisions, then all we have to do is this logarithm thing. Did I see a question? Yeah, okay. So here, the logarithm is just, it's like doing division by 2, but like we're doing that a bunch of times. So the log is like kind of like the opposite of like to the power of in this case. So we're going to divide by 2. So how many times, like what's the relationship here? So the relationship is log base 2 of n. So if n is 1024, the amount of work I'm doing is 10, worst case scenario. Now, okay, let's take a step back and think about the linear search. With linear search, I have to look at n things, worst case scenario. And if I double n, so if I look at 2 times n things, I look at twice as much stuff, right? The amount of work that I have to do doubles if I double the input size. Let's see what happens when I double the input size of something like binary search, something with this log base 2 relationship to the input size. It's 11. With this logarithmic relationship, if I double the size of the input, I only have to do one more thing of work. Where with the linear, I have to do twice as much work. That's amazing. It's not even, so here's the interesting thing that computer scientists care about in this situation is obviously we care about the total amount of work dependent on n. But often what we're more interested in, and maybe I shouldn't say more interested, but often one of the key aspects of this, like, well, how much work is being done, isn't so much on how much work is being done. It's how does the amount of work I have to do change relative to the input size? So with linear, I have to double the amount of work. With log base 2, I only have to do one more thing. Fantastic. And then when you remember with constant time, if I double the input, it's still one thing. So log base 2 algorithms are way better. Like, they're just way faster. This is fantastic. But of course, the catch is this depends on the data being sorted. If the data is not sorted, we can't do this algorithm, because I can't guarantee that all the numbers over here are bigger than this number and all the numbers over here are less than this number. I can't make that guarantee, so I can't play this special game. I can't do this special algorithm. So we have to sort the list. So I mean, if we're trying to think of the total amount of work being done, linear time, n, linear search, linear time, that's like n, and binary search, log base 2. So this is way better, this is slower. But I suppose the question then comes down to, like, how much work is it to sort these lists? Like, how much work is it to sort these numbers? Like, if you imagine, I mean, if I'm starting with an already sorted list of data, I can do this binary search, fantastic. But if I have this unsorted data and I want to do binary search, I have to sort it first before I can do that. And how much work is sorting? We're going to come back to this question. Any last questions before I move on to the next little bitty thing? And then I think after the next little bitty thing, we're going to talk about sorting. So any questions about this binary search or this, like, how much work is being done? Just raise your hand or type a question or whatever. All right, I'll assume everyone is A-okay with binary search, at least the intuition here. Remember, everything from here to the end of, like, next Wednesday, it's not on the exam. It's good to know, especially if you're going to take 162. What if it isn't a multiple of 2? Okay, we'll come to that in one second. What was I saying? That really good question just threw me off, but I'll come to that question in 1 second. Right, everything from now to the end isn't on the exam. So the takeaway I want you to get from these lectures is that you get the intuition and you get the ideas. Understanding the nitty-gritty, if you're interested, you can learn them. But the point is, let's look at these clever ideas. Let's see where computer science can go. Because, you know, first year, first semester, we're programming, yay. But I mean, there's a lot more interesting things out there, in my opinion. Now, your question about if it isn't a multiple of 2. Well, in that case, this relationship still does hold. But let's say I had 1025 numbers, okay, 1025 numbers. After I do that log base 2 thing, I won't be left with, like, it's not a nice clean whole number. You know what, let's go over here. Let's say I've got A equals 1025, and then where do we got? A equals A divided by 2, what's A? I think I can do this. Do it again, 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 do it again. Okay, so if we do that, we're left with 1.0009765,625. So this isn't going to work really nicely with nice round numbers with this guessing game. Another way you can think of it is, if I have 1025 numbers, I'm guaranteed to have 1.00097 numbers left. As we make A a little bigger, let's say I make it just 2000. And then let's just keep doing this. There. Here, if I do this, I'm left with like 1.95 numbers. I know it's a fraction, but think of it, imagine I'm doing rounding such that I'm guaranteed that these are like whole numbers. In this case, I'm left with 1.95, meaning that if I'm rounding, I'm probably left with like 2 numbers. So after this many guesses, I'm not guaranteed to know which number you have. If I do it one more time, like sure, I'll be guaranteed, right, with rounding and whatnot. But before, I'm not guaranteed. Long story short, it's not that it's critical that it's a multiple of 2. It's that the multiple of 2 makes this a little easier to understand. We can talk a little bit more about this next semester in terms of the nitty-gritty mathematics. But if you wanted, you could probably convince yourself of this a little bit more with some pencil, paper, or just what I'm doing here with some code. But yeah, the point is, with a nice multiple of 2, I'm guaranteed to do it in the minimum number of guesses for the largest number possible, if that makes sense. It was just more a way for me to impress you slightly more. Other questions? All right, just feel free to type the questions in the chat because I can hear like the bing if it shows up. But let's move on to, oh, not here, to here. So a lot of people wonder, okay, so we've learned Python. But like, you know that there's a bunch of other programming languages out there, and there's a lot. I mean, many of them are completely, some of them are like joke programming languages. Some of them are more useful than others in certain situations. Some of them are almost always useless. And if you go look at the list of most popular programming languages, let's have a look. Most programming languages 2020. Let's see, what do we have here? Northeastern, let's see. This is like the website to look at this for which numbers or what's the most popular. So as of 2020, C is back on top. Last year it was number 2. This year it's number 1. So it is the most popular language. Then we have Python. Then we have Java, then C++ and C#. C# and Java are very, very similar. Visual Basic, that's a very easy programming language. And I mean, there's a lot of other things as we go down. But you can see that the most popular languages here, you know, C, Python, Java, C++, C#, whatever. One thing we'll notice is all, like, those programming languages are all very, 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 very similar. And I'm going to try to convince you right now of how similar these languages are. The point of similarity between languages isn't that their syntax is all the same. The syntax will differ a little bit between language and language. Why? Just because. Where the differences show up, like what makes a programming language very different from another programming language, is like the way you program. So here's what we're going to do. Let's have a look at Python's linear search. This algorithm should be like second nature to you at this point. Define linear search. It takes the list and the thing we're looking for. For I in range of the length of the list, if a list at location I is equal to the thing I'm looking for, return true. If we ever get to that end of that loop, like we look at all the things in that list, return false. We know it's not there. Great. Here's a linear search in Python. Great. We know it. We're happy. Yay. Here it is in C++. At first, you might think, whoa, that's different, but it's not. Let's have a look. Okay, there are a couple of things that are like new to you. Like you're seeing this like bool here, and then these like ints, ints, int. C++ is a strongly typed language, meaning that if you ever have a variable, or if your function ever returns something of a particular type, so here, true, false, those are Booleans, we have to tell the function, okay, you're a function, and you're going to return a Boolean. That's what that means. In Python, we don't need to do that because Python just figures it out for you. And here we're saying, okay, well, a list, that's a list of integers. It's actually an array, but you can think of arrays as lists for our purposes right now. So we've got an integer here. We're saying it's like a list, an array of integers, and then we're taking an int n and then an int thing. So this is the thing I'm looking for. This is the list or array. But I've also included this n here. And the reason I need to include this n here is because in C++, arrays are really dumb. Arrays don't know how long they are. So I need to kind of know beforehand how big my array is. But it's then on the next line here, this right here equates to this line right here. So what this is saying for I in the range of that thing, and we know that this is going to start at 0 and go all the way up to the length of the list -1. Here, we start I at 0. Well, I is less than n. N is the length of the list. I plus plus. I plus plus is the same thing as I equals I plus 1, or I plus equals 1. It's the same, it's just another shorthand. So this line right here, it's just a slightly different way of writing this right here. It's the same. And then here we see if a list at I is equal to thing, if a list at I is equal to thing. That is like identical. Okay, we've got some parentheses and this squiggly bracket instead of a colon, I guess. But other than that, the if statement's the same. And if that condition's true, return true. Otherwise, outside the for loop, return false. You'll also notice that we need to end some lines with semicolons here. That's typical in a lot of other programming languages. And you'll also see that we have like these squiggly brackets. So this is an open and this is its close. This is its open, this is its closed, this is its open, this is its closed. So in C++, we use these squiggly brackets instead of indents to specify what's where and whatnot. But the point here is, look how similar these languages are. I know, like at first, when you've never seen C++, you think, oh no, it's different. But if you really look at this, the algorithm for linear search, it's the same here. And to me, it's clear as day. Like, yeah, it's the same. Define the function, iterate over all the things. If it's the thing I'm looking for, return true. If I ever get to the end, return false. It's the same. Just the syntax is slightly different. Other than that, it's very, very similar. Let's look at Java. Java actually is kind of like somewhere between Python and C++, I suppose. In fact, ignore public. Just ignore that. I kind of wish I didn't put that there because it's not even necessary necessarily. So Boolean, okay, instead of bool, we say Boolean. Okay, great, because this function's returning a Boolean, true or false, linear search, an integer array. So the syntax is slightly different from C++ down here, and then int thing. We're lucky because arrays in Java know how big they are, so we don't need that n. But otherwise, for I0, I is less than the length of that list, I plus plus. If this is that, return true, otherwise false. Look. With the exception of Boolean being bool in C++, public, which let's just ignore that, and arrays knowing how long they are, and I guess putting this bit here, it is identical to C++. It's the same. So sometimes people will ask me, like, well, how many programming languages do you know? And that's kind of a weird question to ask because, I mean, if you know Python, and you've been using Python a bit and you're an experienced programmer, and let's say you've never used Java before. If I sat you down and said, okay, you got to go write some stuff in Java, you could sit down and figure Java out, and it won't take you very long. So have a look. Like, these are all so similar. Now I'm going to show you a language that's very different. Here is a language called Haskell. It's called a functional programming language. And the funny thing about this language is we're not allowed to have loops in this language. There's no loops allowed. But as I'm certain you will see, this code looks very different than Java, C++, and Python. Look how similar these are, and then what the hell is this? What's going on? So let's do a quick question. Hit the raise your hand button if you think, yeah, what the hell? Okay, everyone put up your hand to make me feel better. Of course, this is weird. This is very weird. So let's look at what this means. Because the reality is this is actually really intuitive, but it's weird. And I really like it though. So here, let's go here. I'm gonna open up Notepad++. Let's do another one there. Move this over here. Okay, great. Okay, so first we have to kind of decode what the syntax means, and it's not too bad. This first line is basically like the first line of any of these other ones. It's the definition of the function. So we're defining the function linear search, and it's like an equation of like on things of type A. Okay, let's say. So it's saying it's a definition of the function. And what it does is it takes a list of things of type A and a thing of type A, and it returns a Boolean. See, a list of ints a thing of int, and then it returns the Boolean. Now, what's cool about this in Haskell is A can be any type, as long as if A is like int, then all the A's are int. So this would be like a list of ints, and an int, it returns a Boolean. But if A is like a string, then it would be a list of strings, a string, and a Boolean. So A is kind of like a stand-in for any arbitrary type, but all things A must be the same type. Okay, so that's just the definition. Before I move on, raise your hand. Raise your hand if you have any questions about that, because I'm about to get to something weird, but also not weird. Totally intuitive, but weird. So ask a question now if you have it before I move on to the potentially more hairy stuff. Okay, so it looks like we're okay. But again, as always, just type the, oh, here we go. What determines the data type of A? It's when I call the function. So in this case, if I were to call the function, like if I were to say, let's say it's already defined, I would call like of, I don't know, some list of integers that just, it's just when I call the function, it automatically kind of figures out like, oh, that's like a list of integers. So this is of things of type integer, let's say. That's all. Okay, so this is perhaps the easy part. This is saying, okay, if we ever call the function linear search and I see an empty list that corresponds to the list I'm looking at, and I get an empty list, and this underscore here means, and I don't care what. So if I call linear search and I see an empty list, then the answer is false. Let me put it this way. Let's say this is my list. And I'm looking for the number 55. Is 55 in that list? No, of course not. It's not. There's nothing in this list. So in fact, I don't care at all what this is. If I ever have an empty list, I know, I'm guaranteed that the thing I'm looking for isn't in that list. Does that make sense, or are there any questions about this? Because understanding this little fact is so critical to understanding how this algorithm works. It's just if there's nothing in that list, then anything I'm looking for in that list isn't in that list because it's empty. Right? I'll assume everyone's okay, but as always, just, you know, type your questions. Okay, so linear search, if I ever look at something like that, and I don't care what, I know the answer is false. So that's the second line. An empty list does not contain the thing I'm looking for. It can't. So now here's the magic. This line right here is the magic. This syntax means this whole list. And Y is the thing I'm looking for. What this means here is take the head of the list, the very first thing, and then the remainder of the list. So let's say I've got the list like 5, 4, 8, 5, let's do like 9, 10, 6. Okay? What this means is turn it into something like this. We get 5, and then we also have 2, 8, 9, 10, and 6. Okay? So this is X, X, S, whoop, colon, where in this case, after doing this, X is 5 and XS is the rest of that list. So this bit right here. Okay? So this is just a fancy way of saying, take the beginning thing out, take that head out of the list. Take the first thing in that list out of the list. The head of the list, take it out. And then take whatever's left in that list and make it like its sublist. Like just make a new list out of the remaining part of the list. Any questions about this? All it means is, yeah, we've got a list, take the head thing out of the list, Okay, so we take it out, and then the remainder part of the list is still a thing. It's just there. So if we look at the code, it says take this and y. Then I ask the question, if x equals y, if x is the thing I'm looking for, so let's say in this case, I'm looking for y is 2. For simplicity, we'll do this. If x is equal to y, that's true, and then so like return true. Or do a linear search on xs and y. Now, what does this mean? There's no trick here. A lot of people, if they see this type of code and they think, whoa, that's weird, this is so different. No, it's not. We're following the exact same rules here. Call the function linear search, okay, on the list. So here I was calling like on this list and 2, right? Now I'm going to go down and call linear search on what? XS. Oh, well, XS is this list right here. It's basically the old list, just excluding the head of that list. And we're looking for 2. So what do? Well, we'll take here. So y is still 2. And then this is now 2. And, well, we get rid of that because that's the head of this list right here. And I ask the question, is x equal to y? Well, in this case, it is. So boom, true, we found it, done. Great. Now let's go back and pretend I'm looking for the number like 22. Okay? So in this case, it's still not there, right? 2 is not equal to 22. So what do? Well, we call linear search on, so this is still 22. I guess I should fill these in so it's accurate. There we go. And we take the remaining bit of this list, which is this. This is XS now. And we call the function. Okay, it's great. So now we just go back in here. But now we've got 8. And this is the remaining part of the list. Does 8 equal 22? No. Well, do it again. We're getting close. We're getting close. Great. Okay, that's not it, so do it again. Wait a minute. Ah, that's 10. Wait a minute. 10, okay. There. This is right? Did I mess up? 8, 9, 10, 6. Okay, great. Okay. So we're almost running out of stuff here, right? So do it again, but now we're just on the list 6. Now here's the funny thing. Whoop. Hit a button that I shouldn't have hit. Here's the funny thing. In this case, x is now 6. The head of the list is 6. And now here's perhaps a trick, but not really. So if I take 6 out of that list, what am I left with? And the answer is not nothing. What I'm left with is a list with nothing in it. I'm left with this, okay? Because 22 is not 6, and the tail of the list of 6 is a list with nothing in it now. So I'm going to call linear search again on this because I haven't found it yet. And this is what I called it on. X is, now wait a minute. Wait a minute. Does this look familiar to you? Linear search on an empty list and something. We now have this space, this condition, right? If we ever call linear search and we have an empty list, I don't care what you're looking for, that thing ain't in that list because nothing's in that list. So I return false. And then we go to the calling function, which was this, and we just return the false, 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 all the way up to here. So we kind of had to go all the way down, answer, okay, it's not there, and then go return false, 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 boom, done. Now we know that thing is not in the list. Raise your hand if you think that's cool. Do me a favor and everyone put up your hand because it certainly is cool. Fantastic. And I'll just assume those that hands aren't up, you're just not paying attention. Raise your hand if you're like, wait, what? Because that's also a very reasonable response to what you just saw. Okay. One honest person. Okay, that's fine. It's a little weird, but the point is, so this is called recursion. And recursion's, I don't know, really interesting. It's fantastic. It allows us to, it's kind of like doing a loop without a loop, right? And I mean, we were able to iterate over the contents of that list with recursion without a for loop. That's great. Recursion also tends to be a thing that throws new computer science students for a loop a little bit, but the reality is we're not like, I think the only reason people have a really hard time with it is because a lot of people are told about recursion before they learn it, and they're told, oh, it's hard, it's scary. It's really not that bad. All you have to do is follow the rules. There's no silver bullet here. There's no tips and tricks on how to understand it. It's just, what does the code say? Follow the rules. There's no new rules here. What does the code say? So that is an example, tongue-tied. That is an example of a recursive linear search, which is fantastic. Anyways, it's 12:05, so we'll wrap up. So that's it for today's class. Thank you to the 20 people, I guess 19 people that showed up, and see you tomorrow. How do I stop the